So last week we discussed the theories of circular motion. So now let's say we have an object moving in a circular path, for example, something like this, right? So for object to move in a circular motion, we state that there should be a centripetal force to keep that object in a circular path. To keep the object in a circular path, there must be a force, a centripetal force is acting on the object. So now here the object is this ball, right? So the centripetal force, the required centripetal force to keep this object in the circular path is the tension acting on the ball from the sting, right? Okay, so, and we can write using Newton's second law, Fc, let's say centripetal force is equals mass of this object times centripetal acceleration. We can define something as centripetal acceleration, whereas the centripetal acceleration is given by AC is equals to V squared over R, where R is the radius of this radius of the circular motion. So here in this case, this length will be R. This is R, or the radius, and then we have V, that is the tangential velocity. Tangential velocity. So I can mark something like that. Where this is V is the tangential velocity. Okay, and also I can write, we know V equals R omega. If let's say this is moving in a constant velocity omega, so we can write V equals R omega. Therefore, AC is equals to, I can write R omega squared. Instead of V, I'm using this R omega divided by R. Therefore, centripetal acceleration, we can write R omega squared. Okay, so we can use either one of these formula to obtain the centripetal acceleration. Okay, good. So these things we studied in our last session. So these are the basic theory of circular motion. Okay, now today we are going to discuss some of the examples in circular motion. So first let me clear all this. Okay, so the first example is riding a bike in a smooth horizontal circular path. Okay, smooth horizontal circular path. So for example, now I can weave the path, this circular path from the sky or from the above. So it will looks like this. Okay, so this is weaving from the top or above from the path. Okay, so in this path, let's say there is a bicycle is moving in a constant velocity omega. Okay, so here I mark. Okay, so this is bicycle from the top, and it is moving with a constant velocity, angular velocity omega. Okay, and let's consider the radius of this path to be simple r. Let's take simple r to be the radius. take this point O, the center of the circular path, and the mass of the bike I consider M, and then the tangential velocity. Tangential velocity, I'm going to consider that is V. So the magnitude of this tangential velocity is a constant because angular velocity is a constant. So here omega is a constant. It's considered constant case, constant angular velocity. So if omega constant, here radius is also constant because this is circular path. So the distance to any point on the circumference from the center is the same because it is a circle. So according to this formula, V equals R omega. R is a constant, omega is constant, therefore magnitude of V is constant. The magnitude of V is constant, so here this is the V, but the direction is changing. So direction changing means this is experiencing some acceleration, which is actually centripetal acceleration. Okay, so yeah, now this is the situation. Now what if we look at this from another point of view? I mean the bike, so this point of view from the above, right? So looking at the situation from the sky, something like that, like from a drone camera. So if I look at the bike from like a background direction, so it would be look like this. So here let me draw the this thing, ground. So it would be like this because this is smooth horizontal, therefore the flow is horizontal. Okay, and now here I'm going to mark the forces or the free body diagram. So I'm going to mark the forces. It would be good in red color. Let's take red. Okay, so now here if you mark the forces, the weight will be vertically downward from the center of mass, from the center of gravity actually. The weight so is vertically downward from the center of gravity of both bike and the rider. Okay, and the normal reaction force will be like this. So if I mark only these two forces, so there are only these two forces, let us mark here. This is mg and this is r. So now we know in order to keep an object in a circular path, there should be a force acting towards the center, or centripetal force. There must be a centripetal force. Now in this situation, where is the centripetal force? Let us think. Where is the centripetal force? Because these are acting vertically. We want something, some force. Let's say this is the O is in this side. Okay. So we should have a force acting this direction, no? So where it is? Therefore, the catch is, the key takeaway is that we cannot go in a circular path if the road is smooth. There should be a friction in order to keep in a circular path, or in order to take a bend, we should have a friction in the flow. Otherwise, we cannot move in a circular path or take a bend or turn, right? In order to turn or bend, or bend means, I mean, like a path is bending. So in that path, to keep the continuous riding, so there should have a friction in the flow. So let's then write it down here. Okay. So I am going to type my topic, edit my topic as riding a bike in a rough horizontal circular path. Okay. Okay. So now it is clear to us that the bike cannot go in a circular path if the flow is smooth. Okay, good. Okay, and then next thing, now let's say the flow is now rough. So let us mark the force here. So let's say this is ground. Do here. Okay, so now the flow is rough, and let's consider the force, the friction on it is F. Because as the bike ride this direction, it's a circular path, it's moving this direction. So what happens? It tends to slide away from the path. No, it tends to slide away from the path, right? So it tends to slide this direction. Therefore, the friction will be in this direction. Is that clear?
Okay.
Altaf, is that clear?
Yeah.
Okay, good. Okay. So, so now we mark the friction in this direction, and let us consider the static friction coefficient, nu s. Okay, so static friction coefficient of this tire and road contact, let's consider that it's nu s. So nu s is the static friction coefficient. Okay, because this is not a kinetic, even though bike is moving, bike is continuously riding with and constant angular velocity omega. Now in instantaneous movement, so something like here, if I consider the bike is here, okay, what would happen, right? What happens here? So if I consider the velocity, so we have velocity in this direction, vertically upward according to the screen. Okay, but still keep in mind this is a top view, so this like maybe not upward, it can be like north, something like that. Okay, something like that. Okay, so this north south. Okay, something like that. Okay, so there is a velocity in this direction, but there is no velocity in this direction, right? So it is in static condition, right? Because it is in a static condition, that means the forces have balanced, right? So forces have balanced. We will come to that there. So here in this direction, the bike is in equilibrium, kind of a equilibrium, right? So it is static. Therefore, we have to consider static friction coefficient. Is that clear?
Okay.
Okay, good. So now the next thing, now I have drawn the bike like this, right? I have drawn the bike like this. And is this picture is correct? I mean, practically, is this picture is correct? The picture here, is it correct?
The forces mapped are correct.
Forces are correct. Okay, the force acting from the points, they are correct. I mean, I'm asking the picture how this bike is it vertical? Is it correct?
Or it should be the other way.
The bike should be bent, no, little bit slide tilt, no, because if you have ride a bicycle, you may know when you turn, you bend, no, bend towards the if you are taking this direction curve, so you will bend this direction, no? Right? Because if I consider the bike vertical like this, so I consider this point, let's say G, center of gravity. Let's consider this point is G, center of gravity. So if I consider the moment about this point, if I consider the moment about this point, what would have now this normal reaction force that is kind of acting vertically, so we can avoid so it won't come. But due to this force, and we have some distance from here to here, no, right? So there is some distance from here to here, right? So force times perpendicular distance, what will have, we have a non-zero torque. So due to this torque, what would happen is this bike tends to fall this direction, right? Bike will fall this direction. Obviously it's going to be fall if you keep vertical when you're taking a bend, right? If is that clear?
Yeah.
Okay, so now I'm going to rearrange this picture. Yeah. So okay, I want to okay. That's pretty good. So here let's mark the forces again. Or else I can start here. And normal reaction force from here. And center of gravity here. And the friction from here. So now if we consider this, okay, here the friction, if I take the torque from point G, which is the center of gravity, so if we consider the torque from point G, so we have taking the torque from G, we have clockwise direction, we have force into some distance, let's say some h1, perpendicular distance from here to here, h1, and then we have anti-clockwise minus r into, now this one has some perpendicular distance h2, r into h2. So these two counterbalance so that the net torque will be 0, so that bike doesn't topple, right? So this is the stable configuration, right? Is it clear?
Yeah.
Okay, so now the picture is correct. Okay, now we can consider this situation and use Newton's second law Okay. Okay, so applying F equals ma to the bike. Now bike in the sense bike and the man. Okay, and man applying F equals ma towards the center. I can just put O because I have already marked. Okay, so if I'm going to apply F equals ma in this direction, so F equals to m mass, and the acceleration is, we know, v squared over r. R is the radius of the circular path. Now here F is the friction force. So now here I can write F equals okay, I'll keep it that as this. So this is F. So I take this is equation number 1. So here I put F directly the friction force. So the required centripetal force is provided by the friction. So F equals mv squared over r. And then I'm going to consider the vertical equilibrium. Considering the vertical equilibrium. So considering the vertical equilibrium, we have R equals mg, no? So let's take this g. Okay. So we have R minus mg equals 0, or R equals mg. So I take this is my equation number 2, right? So that is my equation number 2. Okay, and I'm going to use this area. So I erase these parts. So now I'm going to divide equation 1 by equation 2. So that gives F over R equals to mv squared divided by simple r, the whole thing divided by mg. So we get F over R is equals to, here m cancels off. So we get v squared over rg, right? Okay. So we get one relation that F over R is equals v squared over rg. And we know that fact that is this thing. We know F over R is always, or else I can start from the very basic thing, not from F over R, but from F. F is always less than or equal Fs, where F is the static kinetic friction. Do you have any idea about Fs?
No.
No. Okay, so in friction, the maximum friction that can take is between two objects. Now, for example, now here the rod and tire is in contact, so the maximum friction can take place. The maximum value of the friction can be Fs, right? I think haven't you studied friction, tension, and gravitational force, these things before?
Yeah, dynamic friction for static, and then
Yeah,
limiting.
static friction. So dynamic friction is when the object is sliding, okay, but or moving. But here the object is, if you consider in this direction is object is static. It's not have any velocity in this direction. Even though it's moving, it has a velocity in this direction. So in this direction, it is kind of static, right? It is not moving. So what we can do here is, now for explain that, I consider here, I'll explain you briefly about the friction. So let's say we have a box, okay, placed on a rough surface, and I'm going to apply a force F, let's say in this direction. So I mark that force F. Okay, so let's say I'm going to increase the force F from 0. When F equals 0, there is no any tendency of motion of this object. No, so the object is rest like that. So in that case, will be there a friction force? Will there be a friction force if F equals 0? If F equals 0, then no tendency of motion. No? So there is no friction force. No.
Okay.
Right? Is that clear?
Yeah.
Okay, so when F equals 0, no friction force. But now imagine I'm going to increase this F gradually, slowly and gradually. So let's say I'm going to now force is something like 1 Newton. Still the box is not moving. That means according to Newton's first law, there should be an equal and opposite force, no? So that force is nothing but the friction acting on it. So I'll mark that. So here the friction, so that is F. So in this case, so F equals F. So friction force, this is friction, is equals to applied force, right? So applied force. Now I keep increasing. Now 2 Newton, still the box is not moving. Imagine you have a table in your school classroom and you are trying to pushing it, right? You are increasing your force, still not moving, right? What you do, you increase the force, no, push, right? So you keep gradually increasing, but at a certain value, it suddenly slides, no, right? So that moment where the equilibrium breaks, so it just passed the maximum friction value. So this friction can have a maximum value, F maximum. So that is what we use as Fs, static kinetic friction. Okay, so when this force exceeded that value, what happens? This suddenly start to accelerate. Okay, is that clear? Sorry,
I studied it as a limiting friction.
yeah, limiting friction. Yeah, limiting friction. Yeah, exactly. Thank you. Yeah, so it is limiting friction. So limiting friction is, we can write the Fs is proportional to this the pressure or the force between the flow and the object. Now if I keep another object, something like heavy weight on top of this box, so what happens here, the push is becomes larger. So in that case, then the required force is, in order to move this, the required force will be increased. That means the limiting friction will be increased. So that limiting friction is proportional to normal reaction force. Okay, it's proportional to normal reaction force. So we can write F is equals to nu s R, where nu s is the static friction coefficient. Static friction coefficient. Okay, static friction coefficient. Okay, so is that clear?
Yeah.
Okay, so now here we can say that this friction force, the friction force F, is always less than or equal to Fs, because Fs is the maximum value that friction can have. So when F equals Fs, that is the case, limiting condition, no? It reaches to a limiting value. So if it exceeds this value, it suddenly slides, okay? Okay, so do you understand this F is always less than or equal to Fs?
Yeah.
Okay, that's good. So F is always less than or equal to Fs. So that's what I have written here. So in this, I'm going to divide both side by R. Okay, in this formula, F is less than or equal to Fs, I'm going to divide both side by normal reaction force. Right now, from this formula, we can write Fs over R is actually equal to mu s, right? So here now I can write F over R. So instead of Fs over R, I can use mu s. So F over R is always less than or equal to mu s, where mu s is the static friction coefficient of the rod. Okay. Okay, is that clear?
What's that? Other part?
Sorry?
F over R is less than or equal to what?
Nu s, static friction coefficient, because here you understood this formula.
Yeah.
Okay. Okay, did you understand that? Okay. And now here Fs over R. So Fs over R is equals to nu s, no, because Fs equals nu s times R. So subjecting nu s here, we get Fs over R equals to nu s. Is that clear?
Okay.
Okay, so instead of Fs over R, I can use nu s. So which is the static friction coefficient of the rod. Is that clear?
Okay.
Okay. And I'm going to have this place while I erase this. Okay. So now I can write, now here F over R is equals to, we just derived in our situation, F over R is equals to V squared over RG. So I can write V squared over RG is less than or equal to mu s. So we can subject V squared, then V squared is less than or equal to mu s RG. So we can write finally V is less than or equal to mu s RG, the square root. Okay, is that clear? Altaf? Okay. So now what it tells this? Now this tells us that in order to move in a circular path, there is a maximum value for this tangential velocity. If this v is exceeded that particular value, what will happen is it breaks the equilibrium, or it just break down and go away. I mean, it breaks from this circular motion. It will, I can say, it will deviate, or it will fly off from circular motion. Now you may have seen, watch this Formula One, not Formula One, Formula for car races, but that the bike races. Have you seen in TV?
Yeah.
So in some, you may have seen some bikes skids, skids and go and hit the rail or the wall, right, side wall, right? So it is because what happens is it the velocity is increases that particular value, so that they break down that equilibrium. So actually equilibrium means in this case equilibrium, but we cannot use here equilibrium. This object is not in equilibrium because it's experiencing a centripetal force, right? But anyway, if in this picture, it's kind of have a equilibrium because due to the motion, this bike is tends to skid this direction. Let me mark. So due to the motion, this one will try to skid in this direction with the magnitude of mv squared, mv squared over r. So that thing will be counterbalanced by this friction force. So it's kind of a equilibrium, even though we cannot use the word equilibrium here. Is that clear?
Okay.
Okay. So that centripetal force, centrifugal force is counterbalanced by the friction here, so that it will remains in equilibrium. So in order to have an equilibrium, it should have a maximum value. Now, for example, let's do an example so that it will be clear. Okay, so I'll give you a question. Yeah, question. Write down what is the maximum tangential speed. So I'm using speed rather than velocity because the velocity is changing. So if I use speed, it is same every point. So better word, I'm using speed. What is the maximum tangential speed for a bike? What is the maximum tangential speed for a bike moving in a circular path, moving in a rough horizontal circular path, moving in a rough horizontal circular path of radius 10 meter, let's say, or 100 meter, 100 meter, of radius 100 meter, of radius 100 meter. Okay, full stop. And in brackets, write down the static friction coefficient of the road, or you can continue as a state, continue this here. So write down, and then the static friction coefficient of the road, the static friction coefficient of the road.
Sorry, wait a little.
Okay.
The car is coming, so the connection is missing. Understand? Can you repeat it?
Yeah. What is the maximum tangential speed of a bike moving in a rough horizontal